Hello everyone, myself Mohsin Namdar. Today our group is here to present the ISA activity 1 of the course Tool Engineering, and our topic name is derivation of merchant circles and solving few numericals on it. My group members is Pranav, Sudham, Aniket and Anjali. The next slide is presented by Aniket Bosni.
In the presentation, question is Adira Taylor's two-life equation performance considering the typical cutting conditions such as cutting speed, material properties, and tool material, and solve numerical problems to calculate the tool life at a given cutting speed and identify the impact of speed on tool wear and machining efficiency. Introduction. In machining operations such as turning, milling, drilling, tool life is one of the most important performance parameters. It depends on cutting speed, feed, depth of cut, workpiece material properties, tool material and coating, cutting environment, coolant or dry cutting. Among these, cutting speed has the most dominant effect on tool wear. The relationship between cutting speed and tool life was first experimentally established by F.W. Taylor. Wear mechanism in machining. During machining, high cutting speeds causes high temperature at tool chip interface. High temperature increase the diffusion, oxidation and wear, increase the wear rate, reduce the tool life. The tool life is inversely proportional to the wear rate. Since wear rate increases strongly with temperature and temperature increases with cutting speed. Then derivation of Taylor's tool life equation. Assumptions of derivation is first one is cutting speed is dominant factor. Second one is speed and depth of cut are constant. Tool failures occurs due to the wear. Tool wear rate increases with temperature. Temperature increases with cutting speed. Then step-by-step derivation of Taylor's tool life equation. First step, experimental observation is from a repeated machining test under constant speed, depth of cut, work material, tool material. Taylor observed that cutting speed V is directly proportional to T raised to minus 1, where T is the V is the cutting speed meter per minute. T is the tool life in minutes and N is the tool material constant. Second step, converting the proportionality into equations. V is equal to C T raised to minus N, where C is the machining constant. Rearranging this equation, V into T raised to N is equal to C. This is the Taylor's tool life equation. Tool material exponent N depends mainly on material properties. Some examples of this: high speed steel HSS has typically value of N is 0.08 to 0.15. Carbide tool carbide material having 0.20 to 0.25. Ceramic material having 0.4 to 0.6. and CPN having 0.5 to 0.7, and second one C machining constants. It represents speed at 1 minute of tool life. It depends on workpiece material hardness. Second one tool material and coating. Third one speed and depth of cut. Fourth one cutting environment. The C is a function of tool material, work material and cutting conditions.
The significance of Taylor's tool life equation. The first significance is predicting the tool life. If we know the cutting speed, we can predict the tool life by the formula T equals to C by V bracket raised to 1 by N. It helps to determine when tool will fail and the tool replacement will be scheduled. The second significance is that the selecting economic cutting speed. If the higher speed is kept, the production rate is increases and the tool life decreases. And if the lower speed is maintained, the tool life increases but production rate is decreases. And Taylor's equation helps to find optimum speed balancing, that is tool cost, machine cost and production rate. And the third significance is comparing tool materials. The higher yield value tends to the better performance at high speed. Example, the carbide tools outdrifts HSS at high speed, and ceramic and CBM suitable for very high speed machining. See the numerical problem on the Taylor's tool life equation. The problem given is a turning operation is being performed using a carbide cutting tool under constant feed and depth of cut condition. The tool life exponent for the carbide tool is n equals to 0.25. During machining, it is observed that the cutting speed V1 equals to 120 meters per minute. The corresponding tool life is T1 equals to 60 minutes. Using the Taylor's tool life equation, the determine first one is the value of constant C for tool work material combination, and second term is the expected tool life T2 when the cutting speed is increased to V2 equals to 150 meter per minute, and third term is comment how the increase in cutting speed affects the tool life. The solution for this problem can be calculated as follows. Firstly, we can write the given data. The tool material is carbide. N equals to 0.25 at V1 equals to 120 meter per minute. The tool life T1 is 60 minutes, and we need to find the tool life at V2, which is 150 meter per minute. The step 1 is to calculate the value of constant C. We can calculate value of C by formula V T raised to n equals to C. The value of C is the 333.6. The next step is to calculate the new tool life at 150 meter per minute velocity. It can be calculated by same formula. The new tool life is approximately 24.5 minutes, and the final answer is the increasing speed from 120 to 150 meter per minute. Tool life reduced from 60 minutes to 24.5 minutes.
What is the effect of cutting speed? As the cutting speed increases, tool life decreases. Then this means the tool wears of thrusters. Then the higher speeds. Then high speed steel, cast carbide, and ceramic. There are four materials of the high speed steel is works at lower speeds and has shorter life at high speeds. Then next is cast iron, performs slightly better than HSS. Then third material is carbide. Carbide can be operated at higher speed with longer life. Then fourth material is ceramic. Ceramic tools can run at very high speed compared to other materials. There are four materials. Then the slope of each line represented by M show how sensitive the tool life is changes in speed. Then the steeper slope tool life drops faster and in speed. Overall the graph shows the Taylor's tool life equation. Then the VT N is equal to C, and compare performance of differential tool material. Effect of cutting speed. Next one is why do we increase at high speed? Then the first is higher cutting temperature. Second is increase the fixed friction, and third is thermal softening of tool. First is the higher cutting temperature is temperature rises sharply with speed and causes diffusion and oxidation wear. Second one is increase the friction. Then the more sliding and tool chip interference. And third is thermal softening and tool partially significant for HSS tool. Then next is wear mechanism at different speed. Then this cutting speed are the dominant wear mechanism, and second is low speed abrasive wear, and third is medium speed and adhesive and flank wear, and fourth is high speed and diffusion and create wear. The next one is the effect of machining efficiency. Efficiency is productivity and trade offers. There are higher cutting speed with more material removal rate, that is MRR, and frequently tool replacement and reduce machining time per component. And next is increase the downtime. Then the increase the production output, productivity, and trade-offs one is higher cutting faster. Then the downside of aggressive cutting speeds, then the high speed, high productivity, short tool life, high temperature, and risk of tool failures. Then next is low speed, lower productivity, long tool life, and lower temperature and stable operation.
Effect on machining efficiency. First is low cutting speed. Low cutting speed, what happens is the first is formation of bullet of edge. Second is poor surface finish. Third is roughness, rough surface structure. Second point is moderate cutting speed. What is happen is the stable cutting. Second is minimal bullet of edges. Third is best surface finish. And third point is very high cutting speed. First is tool wear increases. Second is vibration and chatter. Third is surface roughness increases again. Next point is strategy to optimize tool life. First is select proper tool material. It is the choose tool based on operation carbide, ceramic and coated carbide, or it is coated carbide to improve heat resistance and life at high speed. Second is optimize cutting speed. There is a use of Taylor's equation to find economic speed for maximum efficiency. Operate at optimal speed and not maximum to balance life and productivity. Third is use cutting fluids. There is a reduced temperature and friction at the cutting interface. Use minimize tool wear and improve surface finish. And fourth point is control feed and depth of cut. Feed affect tool life more than depth. Reduce feed if wear is high. Use extended Taylor's equation is Vt raised to n into F raised to A into D raised to B. Fifth point is applied tool coating. There is coating like tin or aluminum oxide. Reduce friction, increases thermal resistance and extended tool life. Sixth point is CNC monitoring and predictive maintenance. There is monitoring cutting forces and wear patterns automatically. Adjust speed and stable. Tool replacement efficiency. Slide is industrial application. First is automotive industry case study. Scenario: mass production of engine shaft. Second is using Taylor's equations. First is determine optimum cutting speed. Second is balance tool replacement cost. Third is reduce downtime. And last is rigor. 50% productivity increase. And second is 10% tooling cost reduction.
Then next point is industrial applications. First one is aerospace industry example, machining titanium alloy. Then high temperature and rapid tool wear. Their solution is use ceramic and CDEM tools. Apply Taylor's equation to find set speed, outcome, improve tool life prediction, and control surface finish. Then next is conclusion. The Taylor tools life equation PL is equal to C provides a quantitative relationship between cutting speed and tool life allow the accurate prediction to tool replacement time. Then the second point is tool life decreases expense. Exponentially with increasing cutting speed, affecting tool machining efficiency and surface finish. Then second one is third one is optimization strategies such as selecting the right tool material, controlling speed using applying cutting fluids and CNC monitoring can maximize tool life and productivity. Fourth point is applying Taylor's equation in industrial settings help reduce cost, improve efficiency and maintaining quality, forming the basic for modern machining process optimization. Thank you.